one of our co-organizers, Jeffrey Shallit from the University of Waterloo.
Okay, so I'm going to give a very brief talk, and I think it shouldn't be any more than about 12 or 13 minutes, about something that I discovered recently and puzzles me. And there are probably many experts on these things, much stronger than I am in this lecture. So I leave it to them and see if it's something that's worth investigating or not. So what I'm going to talk about is abelian and additive powers. And I probably don't need to define this, but I will anyway for people who may not have seen it before. An abelian K power is K consecutive blocks, where each block is a permutation of the first block, for example, and hence each block is a permutation of every block. So in English, an example of an abelian square is the word reappear, because the first half reappears in the second half in a permuted way. And the only example I know in English of an abelian cube is the somewhat obscure word deeded, which has 3 blocks of size 2. A word over the, let's say, natural numbers is said to be an additive K power if you can write it as K consecutive blocks, where each block has the same sum. And now I see I neglected to say, and also the same length. So that's very crucial. So each block has the same length and the same sum. So vaccinate is an example of an additive cube if you say A is equal to 1, B is equal to 2, and so forth. So the length of these yi, which is supposed to be all the same in these cases, is called the order of the abelian or additive power. Okay, so let's look at the Fibonacci word. So the Fibonacci word is a famous word that is generated as a fixed point of this morphism. 0 goes to 0, 1, and 1 goes to 0. And then there's a nice paper from 2016 by Ficci, Langu, Lecroc, Lefebvre, Mignosi, Peltomecchi, and Prieur-Gaston. And one of the things that they prove, they actually prove quite a lot in this paper, but one of the things they prove is that the Fibonacci word has an abelian K power of order n somewhere in it, if and only if the floor of K phi n is congruent to either 0 or minus 1 mod K. And here phi is the golden ratio, 1 plus root 5 over 2. So they actually proved, as I said, much more. They proved a more general result for all Sturmian words. So if you want to know the abelian powers, then in words like the Fibonacci word, this is well understood. For example, if you look in the online encyclopedia of integer sequences, then this sequence A336487 consists of those n for which there's an abelian cube of order n in F. Okay, so in particular then, there's actually a finite automaton that accepts these orders for which there's an abelian cube of order n. It follows from the result that I mentioned of Ficci et al. So for example, let's take a look at 12, which in Fibonacci representation is 10101. You start here 10101, and it leads to a non-accepting state. So there is no abelian cube of order 12. Okay, so now more generally, there's a nice paper of Charlier, Rampersad, Rigaud, and Waxweiler, and they, in 2011, they proved that the minimal Fibonacci automaton that recognizes in Fibonacci representation the multiples of K, it has 2K squared states. And they actually proved a lot more than this, but this is one of the things that they proved. So if you combine that with this criterion of Ficci for abelian powers, and you observe that this function that maps n to the floor of n phi is actually computed by a DFA of 7 states. And by synchronized DFA, I mean it takes n and this floor of n phi in parallel in Fibonacci representation and accepts if indeed the function is computed correctly. That shows that the orders of abelian K powers are recognized by a Fibonacci DFA with big O of k squared states. So not that big then. Okay, so now here I'm getting to the question that I wanted to ask, and that's about the Tribonacci word. So remember that the Tribonacci word is this fixed point of the morphism. 0 goes to 0, 1, 1 goes to 0, 2, and 2 goes to 0. And it satisfies a lot of the same properties as the Fibonacci word, and it's been studied quite a lot. And I just as an example, I tried to compute the orders of abelian and additive powers appearing in this word. So remember that the Tribonacci numbers are defined similarly to the Fibonacci numbers, except now each term is the sum of the 3 preceding. And once again, there's a Tribonacci representation like for Fibonacci representation. The difference is that you're writing the ends as 0, 1 sums of numbers, and you're not allowed to use 3 consecutive Tribonacci numbers in the representation. So for example, 43 in Tribonacci representation is 110, 110 because it's T7 plus T6 plus T4 plus T3. Okay, so it turns out that the Tribonacci word can be described in terms of the Tribonacci representation of n. So the nth symbol is 0 if its Tribonacci representation ends in 0, it's 1 if it ends in 01, and it's 2 if it ends in 011. And so that means the Tribonacci word can be computed by an automaton that takes n in Tribonacci representation and outputs the nth bit. Okay, so here's something that I found just by playing around, that there are abelian squares of all orders in TR, and that's actually already known. But here's something that appears to be new, at least I asked a couple people and they had not seen it before. If you consider 2 abelian squares to be the same, if the underlying symbols in each abelian square are the same, that is, x is a permutation of y, and of course x prime is a permutation of x and y prime is a permutation of y, then the order, once you fix the order, there are only 1 or 2 distinct abelian squares in Tribonacci, and both possibilities occur infinitely often. And parts B and C, as far as I know, are new, but maybe someone can tell me if I'm wrong. And then I computed abelian cubes in the Tribonacci word. So so here I was surprised by the answer, and maybe you will be too. So here's the theorem. There is a Tribonacci automaton of 1169 states that recognizes the Tribonacci representation of those n for which there's an abelian cube of order n in the Tribonacci word. And this is minimal. You can't do better than this. So it surprised me a little because I didn't expect it to be anywhere as large. Remember that for Fibonacci, it was like order k squared to recognize abelian k powers. And this is much larger than that. And this sequence of n, it's now in the OEIS, it begins like this, 4, 6, 7, and so forth. Okay, so then I went and looked at additive powers. Here's the theorem. The theorem is that there's a minimal, again, Tribonacci automaton of 4,927 states, recognizing the Tribonacci representation of those n, for which there's an additive cube of order n. And the sequence of these n is this one that I've given here. So you'll notice that it includes, of course, everything for abelian powers, because abelian powers are additive powers. So all the abelian cubes are represented, but a few more orders come up, like 3. And that's also in the OEIS. So these numbers are very large, and to me, they suggest something to be investigated. Now, how did I find those results? Well, you're probably not going to be surprised if you hear that this was done with this theorem proving software named Walnut. And the reason why you can do it is because the Fibonacci word and the Tribonacci word both have this synchronization property, which most infinite words, even simply describable infinite words, are not going to have. So it's very special to this particular thing. So the frequency of each letter in the Tribonacci word is Tribonacci synchronized. And what I mean by that is there's a Tribonacci automaton that recognizes in parallel both n and the number of occurrences of each letter in the prefix of length n in the Tribonacci word. So you could take, for example, there's an automaton that takes n, the number of zeros in the prefix of length n, the number of ones in the prefix of length n, number of twos in the prefix of length n, all in parallel, expressed in Tribonacci representation, and accepts. So that means that we can write first order formulas for any fixed abelian power or additive power, right? All we say is in this block of length 3n beginning at position I, the first n has the same frequency of zeros, ones, and twos as the second block, as the third block, and so forth. And then we can use walnut to compute these automata. So that's what I did, and that's how these results were proved. So now we come to the question and the project, and maybe some of you already know about that. Is there some simpler description of the orders of abelian and additive cubes in the Tribonacci word? Remember, for the Fibonacci word and for Sturmian words, this is very simple characterization in terms of integer parts of some irrational multiple being congruent to something. Is there something similar for abelian and additive cubes and for Tribonacci? And more generally, it would be nice to understand the orders of abelian and additive powers in episturmian words. And is there something similar to this result of Fici et al. That I talked about that there were for Sturmian words? Okay, so that's it. Brief talk, and I'm happy to take any questions.
Thank you. So, are there any questions, comments, and so on? Maybe I will have a question because for the Tribonacci word, I know that you need more than just any line to correctly written in the first order logic. You also have to optimize it. Was it really difficult to optimize the your queries?
No, it was pretty easy.
Okay.
I mean, it takes some computation, right? Because you're dealing with automata with tens of thousands of states, but it runs in a reasonable length of time.
Several minutes?
Yeah, a couple of minutes, something like that.
Thank you.